So thank you very much, Miho, for this invitation. And indeed, today I will discuss observation and some results from the high resolution science, in particular nanoflare prominence, which are the observation that I took care. I've been involved more since the launch of Solar Orbiter. Okay, so okay, so I want to just start to recall in a bit the profile of the mission. I use my mouse here. So you have in this plot, you have Earth, you have the Sun, and in black here is one of the solar orbiter, one of the orbits. So within color here is the period when it was observed with the remote sensing instrument. So there are here also marked the orbit from other assets like Stereo, Bepi Colombo, Parker Solar Probe. So something which is really particular from this mission is that this orbit is that there is a change of the solar distance over time, which means change of the resolution. There is a change with the angle, the Earth-Sun solar orbiter angle, so you can do multi-point of view observations. And now, since few months, we leave the ecliptic, so we are also changing the latitude with respect to, going up in the latitude. So, of course, Orbiter has its own science goal, but now, indeed, we are doing this coordinated observation depending on the configuration we have to increase our science outcome. And I just noted here a few aspects that are that should be taken into account. That depends on what you want to do. So when you, for instance, when you are Earth aligned. When you are Earth aligned, you can do, plasma diagnostics from multiple temperature using, on ground and other assets. When you are an angle which is below the 90 degree, you can do stereoscopic, so triangulation. So you can try to come up with a 3D magnetic structure, measure the heights of the feature from the limb, for instance. And when you are above 90 degree, the angle with the Earth, 90 degree, you can do, for instance, you can do long-term studies using the Earth assets here, and then starting from Earth and then falling with Solar Orbiter. You can do linking science, of course, with the instrument on board, the in situ instrument on board of Solar Orbiter, but also, support to Parker Solar Probe, for instance, or, looking at the far side of the Sun, where you have, you are behind the Sun here. And when you are at perihelion here, this is the place where you want to do a small scale science, let's say, and study the dynamics. So this is what I will as a topic of this talk here. Also, I want to recall the instrument that we are using for this kind of science. So you have the 3 full sun telescope, looking at the photosphere, and UI has 2 channels, the 304 and the 174. And then you have the high resolution telescopes. So you have the HRT on Phi for the photosphere. You have the Lyman Alpha and 174 high resolution telescope on UI. And then you have the spectrometer SPICE. All of them have a similar field of view. This is SPICE, the 2-band spectral band of the spectrometer SPICE, which covers lines from the hydrogen, neutral hydrogen, up to coronal, and then there are a couple of flaring lines, which means that you have quite a wide temperature range. So what we do generally for problem of that data volume, we cannot take all the full spectrum all the time, so we select some spectral windows only to reduce the data volume. Okay, so let's go into the high resolution data. So you have a nice full sun image from EUI with the field of view of HRI EUV, the high resolution telescope here. So what you see when you observe with this telescope. So this is a sequence done at perihelion So which means that you have one pixel about 100 kilometers with a cadence between 2 and 5 seconds. We are in an inactive region, so you see lots of dynamics at all scales. The corona is highly filamented. So really, there are lots of things happening there, and you want to try to understand, explain this, what we see here. Then when you go on the quiet sun, you have something, of course, similar, but it's a smaller scale. This is an example where you have in color here are the dots from all the brightenings that happen in a sequence at like probably 5 seconds cadence of lasting 1 hour. So you see that these brightenings are everywhere, mostly probably concentrated in the in some larger scale, like bright points, and sometimes repeat in the same place. So there's been quite a lot of work done on this feature. I will present them. So indeed, I'm going to show a few results from 3 observing programs from orbiter. So the nanoflare, the pole observation, but I will not do much because Pradeep already covered them, and the what is called the burst program. Okay, so I'm back on the quiet sun with the HRI-UV image and Lyman alpha. So you see all these dots here are all the small scale brightening that has been detected with an automatic procedure, which is published in Bergman's et al. So this was the first, let's paper that highlights the presence of these small scale brightenings. So when you look at the coronal band, you see that they are everywhere, let's say. But when you go, you look at on the Lyman alpha, you see that in fact they are mostly concentrated around the network regions. So there are people that study this aspect too. And this paper provided the first general properties of this event, and that let's say from one side they depends on the parameter that you fix for the detection algorithm. You can change a bit the parameter, for instance, selecting the spatial scales that you are interested in. But in any case, what in this first paper, what has been done, let's say we limit the spatial scale to about 4 or 5 megameters, and in this case, we saw that these events last from few seconds to few minutes, let's say, and they are really all different kind, because this this automatic detection is now based on a physical process, let's say, of something, just on the gradient of the intensity. So everything is you can collect and you can detect everything, let's say, in this range. Of course, you want to know if they are linked, if there is just one mechanism at the base all this variety of phenomena. Okay, so here they are. These are some example what they look like. So as I was saying, you have like loop-like events, you have dots, you have more complex, you have jets here. So you see this is a 6.6 megameter square box, and there are other examples. So this feature, most of them are also seen on SDO AIA, but actually, the tiniest one, if you consider the resolution of AIA, are seen only after that they have been detected on HRI-UV. You have an example here. So this is there is an event here in the 2 high resolution bands that if you zoom in the white square, you see the kind of loop-like that is here in the 174. And when you go on the AIA channel, you barely see it because of the resolution and because of the cadence. So what generally people do is detect them first in HRI-UV and then go back to AIA to see if the event is there or not, because not all the events are detected, are seen on AIA. Okay, so yes, So what I want to start now to show some results, and I start with some statistical properties. So here, this is a nice new paper from Nancy Narang that has been, that I collected a huge amount of brightenings taken at perihelium, so they at 0.29 astronomical units, with this automatic detection. So these are only UI, in analysis only on UI. So you have, you see that there are several quantities, properties, the surface, lifetime, volume, peak brightenings, total brightness, aspect ratio, and several of these properties follow a power law. So this is something that was already known for larger scale feature. Okay, and in fact, if we go back in the literature, we found this kind of behavior for UV brightening. So what I mentioned here in this part, you see how the property of the imager changer over time, starting with SOAT, which has a low cadence and spatial resolution, and going down from AIA and now HRI-UV. So what we can say now is that, so this is an example from AIA, but there are many others, that this event, HRI-UV events, are extend, let's say, these properties, this power law to lower scales. So it's interesting. I think it's very interesting to think how the atmosphere, solar atmosphere, behaves as similarity at all of these scales. Why is that? So there are other works that instead of using the whole database of events detected automatically, as I just showed, that instead concentrate more on one kind of brightenings. So this is the case for what they are called the dot-like event happening in a bright point by Tiwari et al. So they did a statistical work. You see, you have the width, the full width half maximum, which is a bit more than half a megameter, and then you have intensity and lifetime of really less than a minute. They use this information and try to simulate them with a bifrost. And once they were able to find back these statistical properties, they went back to see the magnetic field structure, understand which were the configuration of the magnetic field to at the origin of this event. But I will discuss this a bit later. So this is another example. Instead, these are microjets in the quiet sun. And again, there are the statistical work where, in this case, the only thing is that this population is a bit on the larger scale part of the distribution that we generally have with the Bergman's et al. Automatic detection. But never mind. So it's just it provides you the general means properties of the band, including the speed. I will discuss about this a bit later. So I think this is just to give you an idea what people is doing with this data. And I do also show an example from Corona Hall. This is Pradeep Chitta that analyze this picojet. So when you are here and you zoom in, you see all this kind of dome-like with a spine magnetic feature that are here, where there is lots of flow going off from here. So he, again, with a statistical study, he provided a lifetime, a speed, and energy, and in particular with the speed, he make the strong conclusion that these indeed are good candidates for the fast solar wind that are measured in situ. So as you see, again, these are high cadence, 3 seconds cadence with a spatial resolution of about 200 kilometers. So we are really playing at the limit of the resolution of the instruments. Okay, the statistical work also can be done to provide information, temporal information. And this is, for instance, in the context of corona heating. So we have this one of these theory of the nanoflares or picoflares or whatever that may hit the corona. So the situation is that the observed event, even if we take the smallest one, they are not enough to maintain the corona at 1 million degrees. So we are looking for even, unresolved event or tiny event to see if they have this role in the corona heating. So what you have here is you have as a function of time, you have the number of pixel or number of events during the time sequence. This was done with a UI in the quiet sun by Nelson. And what you see is that the number doesn't change much over time. So you can say, okay, that can maintain the corona. But when you go and count them and you do this an estimate of the energy that they provide, this is a very, very tiny amount. This is they occupy a tiny amount of space and tiny amount of energy. And so what is found is that confirm some previous study that we are still not there. I mean, this there's even the smaller feature that we see in EY, they are not enough to maintain the corona. And in this context, also my former students, Antoine Doliu, did his PhD in, let's say, in this frame, and the idea was to extract some thermal property from these brightenings. And to do this, in this first paper, he used the AIA light curve. So he got the event, identified the event on UI. He went back to AIA, extracted the light curve and cross-correlate light curves from different bands. And what is plotted here as an example is for 171, 193 bands in red. So you have all the pixels that have all the brightenings. So you have the maximum correlation with the time lag. The time lag gives you the delay between the peak in the two light curve from the two bands. Okay, and what you see, this distribution is centered around 0 with a width about 1 minute. So at the limit of, let's say, we are really at the limit of the resolution of AIA with a bin of 12 seconds. And he did also a simulation work to simulate a tiny loop that are heated impulsively and looked at the behavior of the light curve. And what he showed is that indeed this kind of behavior that we have here comes from events that do not reach coronal temperature. So they are transition region events. You can have some, I mean, this behavior can in some cases be obtained only when you put lots of energy, and this produces a very strong flow within the loop, but it's a strong flow which is not observed. So the conclusion is that probably most of these large amount of events, probably most of them are cool transition region. Some of them certainly reached coronal temperature because there is this red distribution has a certain width, which means that there is a delay between the bands, so there is a cooling or any heating going on, but it's not the measure part of them. Also, you see in blue here is the distribution of the quiet sun, so the pixel outside the brightening that you see behaves differently. Okay, so now I move from the statistical properties to show detailed analysis on some of these events, some plasma diagnostics. And this is a generally you do either using EY and SPICE on solar orbiter, or you do this together with other assets like sun Earth, when you are aligned with Earth, so you use the IRIS and other instruments. Okay, So again, I start with a work, the second paper of my former student, Antoine Dodieu, who has put together UI, HRI-UV, and SPICE, so the spectrometer. So you have here on the left a movie. In the red box, you have an event on HRI-UV, and what you have here in white is the slit of the spectrometer SPICE, which is rastering the event. So you have the intensity map that with the temperatures from lines that increase from the left to the right. And what you see is the event clearly seen at low temperature. Why? When you go up in temperature, transition region line, coronal line is not visible. And you see here an example where you have clear signature in the cool line, but in the magnesium line, you don't see anything. So what this means is that this is a cool feature, right? And UI is what is seen is that the cool part of the response function, which has reacting, which is detecting what we see now. Okay. So when you look in detail, you know, at different temperature, the behavior of this feature, you see different thermal behavior. So I show some of them here, still from Antoine work. So you have on the top, you have a light curve from UI, and on the bottom here, you have SPICE from the hotter to the cooler line. So in this event, you have two peaks, which there is no signature in the neon 8 line, while it is clearly reproduced in the cooler line. When you go to this other event here, you have the first peak is seen in the neonate, but not the second peak, while the second peak you see is seen only in the cool line. So clearly there is a multi-temperature behavior here. There are other examples, like this one, where you have the clear signature in the neonate, which is exactly the same as the one with the UI. So you know that this feature is reaching high transition region temperature. But when you can use also iris and ice when you are Earth aligned, because ice is very interesting because it has all this hot coronal line. And in fact, this is an example here. You have a feature from HRI-UV in this point here that you clearly see in the cool line. But when you go up above the iron 10, 11, the feature disappear. You just see a large scale loop, which is here in the coronal heating. So this has no coronal emission. And finally, the final example I want to show you is this one that has, so you have again the event here, the brightening here, and when you go down in the atmosphere with iris, there is no counterpart. So you don't have any signature in the magnesium 2 and silicon 4 line. So so this is only coronal response. So you see, this is really we need, when you want to, I think from my side, when you want to look at this feature, you need to make a distinction, or you know, depending on what we are interested in, between all this population of event. And I go with just one slide on the plasma flow. There is not much work done. You can use iris. So this is an example with iris where you have this feature here, and these are map of the Doppler from magnesium 2 to silicon 4. So this is a kind of loop-like feature, small scale feature that this was Nelson, which identified strong Doppler at the loop 4 points. And during his analysis, he recognized the signature of explosive events. So this means that we knew that many of these features are already known, but now we see them much higher resolution with this instrument. And the final example is when you don't have a spectrometer, you use the time distance map here to have an estimation of the plane of the sky, the speed on the along the plane of the sky. So this is you see there is a kind of a jet here with a slit here, and you see the time and the intensity, and you see you can have an idea of the velocity, and you can produce statistics of this feature. So, okay, so I didn't talk about SPICE because SPICE has an instrumental problem, let's say, that not allowed to do Doppler until now, but there are good news. We are providing soon a tool to make a correction and to do some Doppler, so stay tuned for this. So the link with the solar atmosphere is I finished with these things. So the other things, you can use iris to go down in the atmosphere, like in this case. This is Mandal that was interested in the dynamic fibrils in an active region. So you see, you selected the several fibrils here and put together the time with this method of the JMAP here. He put together HRI, AIA 171, and the IRIS cool line. And this feature that are kind of inverse U that were already known in the low temperature lines are now seen in HRI-UV. So this allows indeed to make the connection between the layers of the solar atmosphere and estimate and say that indeed this feature can reach coronal temperature. Finally, there is the connection with the photosphere. This is a bit more complicated. Yes, there is no a clear picture about this. Kyle has done a kind of statistical work where they selected two groups. Let's say one group who were at the base of the feature, like in this case, is a look like there are two polarities, clear polarities that connect the feature. And they see sometimes there is a dynamic, sometimes they converge, or there is some flux emergences. So all aspects that were known. But also there is a second group where there is not a clear connection with the photosphere. So you have the event here, and there is certainly you have a complex multipolar feature, but it is not clear where this feature is rooted in photosphere. So panelists are also quantified the decrease of the converging flux between two polarities, as is plotted here, and it generally came out with a certain number of properties that are listed here. He found a lot of these features which are above neutral lines with eventually mini filaments. But again, it seems that there is not a real, a standard property of the photosphere below this feature. Like Nelson, for instance, he found that most of his events were above a weak field. So I think there is lots of work to be done. I'll just show you a few examples, but this is something that really has to be developed, studied more. Okay, so I finish quickly with the filaments to give you an idea, a flavor, what we can do with filaments. So this is a movie, a 5-second cadence with HRI UV. At the limit, you see fantastic images, a fantastic movie. And we were in quadrature here with Earth. And there was, after these observations, there was an eruption which was captured by FSC 304 that you have here. In 1 second, sorry, the quality, the movie is not so good. And this means that also AIA saw it because we was facing, you see, the eruption. So you have nice data that you can use. And also SPICE was observing, and here you have two maps in Lima beta before, so at the same times of UI here, and later on during the eruption, we capture the eruption here. And just to give you an idea what can be done, Young et al. We submitted this paper is under revision, where he used the radial velocity was is estimated the radial velocity of the eruption using stereoscopy information that use as an input of a non-LT model, and then use the Lyman beta and Lyman gamma from SPICE to constrain 200 model for the prominence. So come up with this kind of distribution probability for the parameter of the prominence. So I think this is a new diagnostics that he's publishing now. So my conclusion, HRIUV Phi observe regularly now what features that were known already, but they have this advantage that the temporal resolution, the spatial resolution is higher, so we can learn more on them. And also, it is clear that HRIUV also observe a smaller feature that were not observed before. I think it's really important, the coordination, when you are interested in analyzing and doing dynamics at small scale. Spectroscopy, you can do spectroscopy, general diagnostic, but also from 2 points of view. And stay tuned for SPICE. We really hope soon to give you news about it. You can do, multi-layer analysis and 3D information. And I finish. This is my last slide. A bit of advertisement for SPICE, because we have now tools for the analysis in IDL and Python. We have quick tool in IDL and Python. And if you need any information, you want to do some observation, anything regarding SPICE, here you have the email of the team. Thank you very much.
Thank you, Susanna. Stopping the recording.